Welcome to the fourth and last part of section 4.1. So now we will cover how the wave packet techniques, especially using the variational approach, have been used in condensed matter physics. The name that is most intimately connected with applying a variational semi-classical approach are Sundaram and New in 1999. They explained how to derive semi-classical equations of motion for a Bloch electron exposed to an external slowly varying electromagnetic field. And of course, there have been many follow-up works by Sundaram, New co-workers, as well as other people. So there is, for example, a work that does the same for photonic crystals, which are the electromagnetic analog of the systems that we've been covering. So this is a very versatile and very successful method in the physics community. So if you remember the band picture, then I made the assumption that we pick an isolated band that intersects with the Fermi energy. And this is, of course, a strong assumption, but this is just to simplify our lives a little bit, because then we neither have to contend with band crossings, with intersections of two bands, nor do we have to explain what to do when we consider different bands. So this is just a simplification of our description. So you so we shall assume that EF intersects only with a single isolated band. And this band shall be non-degenerate. So the eigenspace associated to it is one-dimensional. So let's see if I can find the sketch. Let's copy and paste. So as before, the band in this picture, the band that would satisfy the assumption is the band E3. So as you can see, the Fermi energy intersects only with the band E3, and the band E3 is separated from the bands above and from the bands below. So mathematical physicists in the business would say that E3 satisfies the gap condition. And what you would like to do is you would like to construct wave packet states. Let me choose red, which are sharply peaked in momentum space. So for physical reasons, you should probably pick states around the Fermi energy. So here, this state is sharply peaked at the intersection point with energy EF, more or less. And the way to describe those states is as follows. So this is equivalent to what I wrote down before, that the psi, so let me call this here psi. Let me continue to use red to indicate the association to the band E3. So one way to write it is to say that psi is in the range of EF minus delta, EF plus delta applied to H epsilon. So again, this delta is chosen so that you only pick out the band E3, but it's small enough, small enough that it doesn't intersect with the other bands, but large enough that it covers the entire range of the band function E3. And okay, if this is perhaps too implicit, there is a very simple other way to express waves of this type. Namely, you say, okay, I'm looking at waves psi of x, which can be written as the k-space integral. So let me also allow this wave to be time dependent. And I'm going to choose a complex coefficient function to, in this case, the Bloch wave phi 3. So this is just a Bloch wave associated with the band E3. And of course, this A has to satisfy a normalization condition. Namely, you're assuming that the integral in Bloch momentum k, in crystal momentum of A of t and k absolute values squared, that this is equal to 1. This is just equivalent to saying that the norm of psi shall be 1. So importantly, so this is of course a deviation from the way a mathematical physicist would handle things, is that they only describe the properties that these A's have. So they think of them something like Gaussians or other types of wave packets, but they do not completely specify, but they do not specify the exact shape. And this will lead to some drawbacks, let's say even from the physics point of view, but more importantly, this means that they cannot make any error estimates explicit. So this is, nevertheless, it's the assumption A of t and k is sharply peaked in k space. So in momentum space, and of course physicists just assume this. Sufficiently regular. So it's assumed to be smooth. Maybe it has compact support. But it's quote unquote nice enough. So this assumption just corresponds to this picture here. So if you want to visualize this, this is what you should visualize. And then as before, you introduce the expectation values of position and momentum. Okay, maybe let me put this on the next page. In the end, these, rather than, if you were coming from the mathematical physics community, probably the way you would read the following equations is that given A, I can deduce, for example, the center in momentum space, but the way it should be read here, and this is not my idea, this is just how it comes out in the paper, is that you should read that Kc, which C stands for center, characterizes the distribution A of T and K, for example. So you should actually read it like that. So you would like, what you vary is the center of the wave packet in momentum space, for example, and then given your preferred Kc, you then pick a distribution A, T of K. So that's how you would go about it, not the other way around. And then there's also an average position. And here you need perhaps a little bit of computation, not a lot. So you would just plug in your state psi. So just as a reminder, this here, I'm just plugging in psi essentially. And then the operator, so after Fourier transform, the position operator just becomes I gradient in K. And this gradient is applied to, well, the product of the prefactor and the Bloch function. And then you take the scalar product over the torus, and this is the real space variable. That's not momentum space, that's the real space unit cell. All right, and that means you get a sum of two terms. So the first contribution is simply I, A of T and K complex conjugate, gradient K of A, T, and K. And because A is normalized, this gradient actually only acts on the phase. So that's perhaps not immediately obvious. I'm just saying it so that it becomes clear that this is just about the phase. And then you have a second contribution. So first you can factor out this guy here, and then times I phi 3 of k gradient in k of phi 3 of k. And the second term is well known in the condensed matter community as the so-called Berry phase. Sorry, the Berry connection. So since there's only a single band, this is just because you have a gradient here, this is a d vector again. And the presence of this Berry connection will lead to what physicists call the anomalous velocity term that is due to the Berry connection. So you can think of A as a vector potential to a curvature, and the Berry curvature is evidently that curvature. And this will enter the equations of motion. And the curvature itself, if you average it over the Brillouin zone, over the torus T star, then you get up to a normalization factor of 2 pi, you get an integer. And this integer is the well-known Chern number. So now let's have a look how to go from the Euler-Lagrange equations to the semiclassical equations. So I'm now using the sketching the arguments of Sundaram and New. What they would say is the parameters RC and KC so they characterize the wave packet. So these are the local coordinates, if you wish. And hence, what you obtain in the end by writing out the Euler-Lagrange equations in local coordinates, meaning in RC and KC, and then this will lead to equations that depend on potentially time. RC dot, so the time derivative of RC, KC, and the time derivative of the center of the wave packet in momentum space. So that's basically how you would arrive at your semi-classical equations. To do the actual computations, this is a little bit tedious, and I will not even attempt to do this here. But basically, the first step that they do is they express the Lagrangian in terms of the local coordinates and then, okay, Euler-Lagrange will give you the equations of motion. But importantly, the actual distribution A is not specified. So that's, of course, a bit of a hurdle if you wanted to make this mathematically rigorous. But of course, what they do is they do actually characterize it. So in a typical discursive fashion, they explain what is going on. Instead of dwelling too much on this point, because it might sound like I'm poo-pooing their methods. I'm not, but it's just something when you want to translate a work of theoretical physicists to the language that is more easily digestible for someone from mathematics, then this is the kind of stuff that you have to figure out. At the end of the day, they arrive at semi-classical equations. Semi-classical because, of course, the band function, for example, as well as other terms that come from quantum mechanics, are retained in the equations, and so you can actually see some features of the quantum nature are still captured in the classical equations. So you have an equation for RC dot, which is, okay, plus the K gradient of a semi-classical Hamiltonian. So we'll write down this Hamiltonian in just a second. Then you have minus the R gradient of the semi-classical Hamiltonian. But now you have two extra terms. One is due to the Berry connection. So this is just omega times Kc dot. And then you have a magnetic term if we include a magnetic field in our discussion. And let us just give the definition. So where omega is the exterior derivative of the Berry connection, but the exterior derivative of this connection is the associated curvature, so that's why it's called Berry curvature. And then there's a second term that I've yet to define, and that is the semi-classical Hamiltonian. So let me color this appropriately so that it's a little bit easier to follow. let's pick orange. So the semiclassical Hamiltonian is the sum of the band energy, so in this case E3, but we're adding a magnetic field. So strictly speaking, this was not included in my discussion up until this point, and this is another hurdle to make this mathematically rigorous. But nevertheless, with other methods, you can derive the same equations, but with mathematical rigor and with a complete understanding how this comes to be. Then, of course, we have to add the external potential that generates the electric field. And then there is a new term, which is the so-called Ramal-Wilkinson term. And there's actually one thing that is missing. This is something that we will add by hand back. So this is discussed in the text, but also they, Sundaram and New, did not include a small parameter in their discussion. But still, they do know that this extra term is a subleading term. So they are not ignorant of this fact, they just don't have the mnemonic device that is our epsilon. And this Ramal-Wilkinson term is defined in term M is defined in terms of the Bloch functions. I will not give a definition here, but the point is this is an explicitly given function. And it gives you a sort of an average magnetization of the states on the band. So this changes the energy depending on the directionality of the magnetic field that is applied. So this is basically their result. They have applied this to other systems. There are refinements and so on and so on. But the basic idea is still the same. So let's do conclude this section by summarizing some pros and cons. So I'm a positive person, so let's start with the pros. And I'm not speaking of the work of Sundaram and New, but of this variational approach at large. So in the plus column, I think one thing you can agree on is that this approach is conceptually very, very simple. And this makes it very approachable. You don't need, at least to understand the basics, you don't need any highfalutin theory or, you really, I mean, it's very, very straightforward in a sense. The second thing, and I'm speaking, of course, of the variational approach here, is that this is algorithmic and versatile. So algorithmic means you can really compute the equations of motion, and versatile means it's not limited to a particular setting. In fact, this idea of a constraint manifold can be used outside of the context of semi-classical approximations. What you can do is you can, for example, derive the Hartree-Fock equations. So here the assumption is that your states are determinantal states, so that your states automatically satisfy the Pauli exclusion principle. If you've seen the Hartree-Fock equations, you know that they're nonlinear, and that's simply because the constraint to determinantal states, the determinant is, unless you're looking at scalars, is a higher order polynomial. So it's the manifold of determinantal states is really a nonlinear affair, and hence it's not surprising that the equations are nonlinear. So here M are determinantal states. And another point that I think is quite nice and very elegant is that automatically the you inherit a symplectic geometry. And as I mentioned, this is related, or one way to look at the problem of semiclassics is that you do symplectic reduction. So, for example, because your position operator, now if you want to have a gauge independent formulation, you should not just look at this term, but really at the sum of this term plus a connection. And so it's not surprising that associated to this connection, you see the effect in terms of the associated curvature. That's the same for the magnetic field, where instead of K, you have to work with K minus A, the kinetic momentum. And once you do this, that your equations for kinetic momentum involve the magnetic field B. And that's the same here. So here you just see it in one particular example. But there are a few drawbacks. I think the first one is that generally speaking, at least if you put your mathematician's hat on, error estimates are hard. Of course, for very simple states and perhaps to leading order, it's possible, but connected to this is that leading order approximations are typically not good enough. Or let's say, instead of typically, maybe that's too hard, but often are not good enough. So for example here, I should have also added the epsilon here. Again, the epsilon is absent in the original work, but we know where the epsilon will be hiding. And this compounds the problem that I first mentioned, because maybe maybe Gaussian states that are correct to leading order and so forth are simple to construct and very explicit, very nice. But if you want to go beyond leading order, you have to correct your wave packets. So what you have to do is you have to propose wave packets with better approximation properties. And these need to be guessed correctly. And both of these points feed back into what I've written before, namely that the error estimates are hard. And once you go beyond leading order, things get very hard. So I think this deserves to be put in red for this reason. So if you, I think if I want to insist on a complete mathematical statement that, for example, these semi-classical equations approximate the full dynamics, I must have explicit control of the remainder. And if I don't think I've completely solved the problem. The last thing is something that can be mitigated to some degree, but involves extra work. And that is, not all states are wave packets. So, for example, if you lift the Fermi energy above this band, but in the gap between the bands E3 and E4, then the band E3 is completely filled. And what you would have to do, so this is the situation in solid state physics, so this is not just, let's say, some hypothetical case. Of course, physicists are not stupid. They know this. They're extremely aware of this, and they would just say, well, okay, then I just have to use think of these guys of wave packets like that as an overcomplete basis, and then just by making sure I count everything correctly and not twice, I can just decompose this filled band into wave packet states like that, and then just by averaging in the right way, I get the right result. That is correct ultimately, but I would say it's still, at the very least, inelegant. So, but nevertheless, let me say this, that this is the case in solid state physics. So this can be mitigated. I think the most successful application of this technique is to so-called Born-Oppenheimer systems, which give you a model for molecules where you exploit that the nuclei are much heavier than the electrons, and then you can approximate the motion of the nuclei by classical dynamics, and you only have to treat the electrons as quantum mechanical degrees of freedom. And For these types of systems, Hagedorn and Joire and many others have contributed work where they took care of all these objections. Also, there it's much more natural to think of wave packet states, because the nuclei, they behave semi-classically, so you can think of them as or link them to Gaussians. And by putting in enough effort, you can also indeed raise the fidelity of the approximation. It's not necessarily easy. If you look at some of the equations, they're quite lengthy and complicated, but it's doable. And I think in terms of the rigorous math literature, this is let's say, these are the strongest results, but I'm not aware of anyone trying to make this rigorous in solid state physics. Instead, the best known result uses a different technique. Or let's say there are two techniques where I know rigorous results exist. One is the WKB approach that I will not talk about because of time constraints. And the other one, in my opinion, the more versatile and successful one, is Wald quantization. And we'll cover this in section 4.2 next.